Our place in the cosmos. A historical perspective. For millennia, humans have gazed at the night sky with a sense of wonder and curiosity. The vast expanse of the cosmos has always been a source of fascination, inspiring countless myths, legends, and scientific inquiries. The stars, in their fixed positions, seem to revolve around our planet. This apparent motion of the stars led early astronomers to believe that Earth was the center of the universe. This observation led to the development of the geocentric model, a belief that Earth was the center of the universe. This model was widely accepted and became the cornerstone of ancient and medieval astronomy. This idea, deeply ingrained in the minds of our ancestors, formed the basis of their understanding of the cosmos. It was a model that seemed to make perfect sense given the observations they could make with the naked eye. It influenced not only their scientific views, but also their philosophical and religious beliefs. The geocentric model was more than just a scientific theory. It was a worldview that shaped how people saw their place in the universe. To them, Earth, as the supposed center of creation, held a place of paramount importance, with all other celestial bodies existing in subservience to it. This belief was reinforced by religious teachings that placed humanity at the center of God's creation. The geocentric model, with its intuitive appeal and philosophical underpinnings, reigned supreme for centuries. It was a model that provided a coherent explanation for the movements of the stars and planets as observed from Earth. It provided a framework for understanding the apparent motions of celestial objects. Ancient astronomers meticulously charted the positions of stars and planets, creating detailed star maps and celestial models. Ancient astronomers developed elaborate systems to explain the movements of the stars and planets, all revolving around the stationary Earth. These systems included complex mechanisms like epicycles to account for the observed retrograde motion of planets. This model was not simply a scientific hypothesis, it was a deeply held belief, intertwined with religious and cultural worldviews. It was a model that provided a sense of order and purpose in the cosmos. The idea of an Earth-centered universe was not challenged until the late 16th century. The advent of the Renaissance brought about a renewed interest in observation and experimentation, leading to new discoveries that questioned the geocentric model. The shift from the geocentric to the heliocentric model, placing the sun at the center, marked a profound turning point in our understanding of the cosmos. This revolutionary idea was first proposed by Copernicus and later supported by the observations of Galileo and Kepler. This shift in perspective not only revolutionized astronomy, but also had a profound impact on science, philosophy, and religion. It challenged the long-held belief that humanity occupied a central place in the universe and opened up new possibilities for scientific exploration. It challenged long-held beliefs and paved the way for a new era of scientific inquiry. The heliocentric model laid the foundation for modern astronomy and changed our understanding of the universe forever. The Ptolemaic system, an Earth-centered universe. One of the most influential geocentric models was developed by the Greek astronomer Claudius Ptolemy in the 2nd century AD. Ptolemy's work was a culmination of centuries of astronomical observations and theories, building upon the knowledge of earlier Greek astronomers like Hipparchus. His work, known as the Almagest, presented a comprehensive mathematical model of the universe. The Almagest was not just a book, it was a monumental compilation of astronomical knowledge, containing detailed star catalogs and mathematical techniques for predicting celestial events. Ptolemy's system was based on the idea of nested spheres, with Earth at the center. These spheres were thought to be made of a transparent, crystalline substance, each one carrying a celestial body. The sun, moon, planets, and stars were all thought to be embedded in these celestial spheres, each rotating at its own pace. This model explained the apparent daily motion of the stars and the complex paths of the planets across the sky. To account for the observed retrograde motion of planets like Mars, Ptolemy introduced the concept of epicycles, smaller circles within the larger orbits. These epicycles allowed Ptolemy to explain why planets sometimes appeared to move backward in the sky. The Ptolemaic system, though complex, was remarkably successful in predicting the positions of celestial objects. It provided a framework that could be used to create accurate astronomical tables, which were essential for navigation and calendar making. Its accuracy and comprehensiveness led to its widespread acceptance for over a millennium. Medieval scholars and Islamic astronomers further refined Ptolemy's model, ensuring its dominance in the field of astronomy until the Copernican revolution. Copernicus's revolution, shifting the center. In the 16th century, a Polish astronomer named Nicholas Copernicus proposed a radical alternative to the geocentric model. In his book, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, Copernicus put forward the heliocentric model, placing the Sun at the center of the solar system. He argued that Earth, along with the other planets, revolved around the Sun. This revolutionary idea challenged the prevailing view of the universe and had far-reaching implications. Copernicus's model provided a simpler explanation for the retrograde motion of planets, which Ptolemy's epicycles had struggled to explain. He showed that the apparent backward motion was an illusion caused by Earth's own motion around the Sun. Section 4, Galileo, Kepler, and Newton, validating the heliocentric model. Copernicus's heliocentric model, while groundbreaking, was not immediately accepted. The idea that the Earth was not the center of the universe was revolutionary and controversial. It challenged centuries of established thought and religious doctrine. It took the work of other astronomers, such as Galileo Galilei, Johannes Kepler, and Isaac Newton, to provide further evidence and solidify the heliocentric theory. These brilliant minds built upon Copernicus's foundation, each contributing crucial pieces to the puzzle. Galileo's observations with the newly invented telescope provided compelling support for Copernicus's ideas. He meticulously documented his findings, which included the discovery of Jupiter's 4 largest moons, now known as the Galilean moons. He observed the phases of Venus, which could only be explained if Venus orbited the Sun. This was a direct challenge to the geocentric model, which could not account for these observations. Johannes Kepler, a German astronomer, made significant contributions by discovering the laws of planetary motion. Kepler's dedication to understanding the cosmos led him to analyze the meticulous data collected by his predecessor, Tycho Brahe. Kepler's laws described the elliptical orbits of planets, their varying speeds, and the relationship between their orbital periods and distances from the Sun. His first law stated that planets move in elliptical orbits with the Sun at one focus. These laws provided a mathematical framework for understanding the motion of planets within a heliocentric system. Kepler's work was revolutionary, offering precise predictions of planetary positions and movements. Isaac Newton's law of universal gravitation provided the final piece of the puzzle. Newton's Principia Mathematica laid the groundwork for classical mechanics. Newton showed that the same force that causes objects to fall to the ground on Earth also governs the motion of planets around the Sun. His law of universal gravitation explained how every mass attracts every other mass, with a force proportional to their masses and inversely proportional to the square of the distance between them. This unified the heavens and the Earth under one grand theory of motion. Section 5. Beyond our Sun, the Milky Way, and other galaxies. As astronomers continued to explore the cosmos, they made groundbreaking discoveries that further expanded our understanding of the universe. With the aid of improved telescopes, they realized that our solar system was just one small part of a vast collection of stars known as the Milky Way galaxy. The Milky Way, a barred spiral galaxy, contains billions of stars, gas, and dust, all held together by gravity. Further observations revealed that the Milky Way was not alone. There were countless other galaxies scattered throughout the universe. These galaxies came in various shapes and sizes, each containing billions or even trillions of stars. Section 6. Hubble's Revelation, the Expanding Universe. In the early 20th century, American astronomer Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. By observing distant galaxies, Hubble noticed that their light was stretched, shifting towards the red end of the spectrum. This phenomenon, known as redshift, indicated that these galaxies were moving away from us. Hubble's observations led to a startling conclusion: the universe was expanding. The farther away a galaxy was, the faster it appeared to be moving away from us. This discovery had profound implications for our understanding of the cosmos. It suggested that the universe had a beginning, a point in time when it was much smaller and denser than it is today.